Hello everyone. We continue our discussion on solution of integer linear programming formulations. In our previous lecture, we talked about the relaxations and their uses. And basically, we said that there are 4 uses of relaxations. We can prove whether an integer program is infeasible by looking at relaxations. We can prove if it is optimal by looking at relaxations. We can calculate some bounds, upper or lower bounds, using relaxations, and also we can get the solution of a relaxation and by rounding the decision variables, which are fractional, to nearest integer values, we can get some feasible solutions again, which will help us to find some upper or lower bounds. Now we are going to use these relaxations to develop algorithms. Basically, in this tutorial, we are going to talk about the branch and bound algorithm, and through a simple example, we will start learning the algorithm. I will split this video into a series of videos, tutorials, so that it will have smaller sizes. In solving integer linear programs, basically we will talk about the branch and bound algorithm and the branch and cutting plane algorithms, 2 algorithms. For branch and bound algorithms, remember, we may have an integer, pure integer programming formulation in which all decision variables are general integers, or we can have a binary programming formulation in which the decision variables are binary, which can take only values of 0 or 1. So, although the main idea is the same, for general integers, the branch and bound algorithm, and for binary variables, the branch and bound algorithm can have some differences. So we will first start with the general variable case, general integer variables. We will learn how to solve those using the branch and bound algorithm. Then I will talk about the binary case, and we will make some examples on this. So let's get started. Okay, in both the branch and bound algorithm and in the cutting plane algorithms, the general scheme is the same. We can talk about 3 steps in all of these algorithms. These are the general steps, and we will talk about their details. The first step is the relaxation. So you have an integer programming formulation, and then we relax it. We talked about this relaxation. We either delete a constraint or make it easier. So in solving these integer programming formulations, the most widely used relaxation is the LP relaxation. So what do? We take every integer restricted variable and relax them. If it's a binary variable, for example, if y is a binary decision variable, we can replace it as, for example, y being between 0 or 1. Or if y is a general integer, then we say that this y should be greater than or equal to 0. We replace it with this one. Okay? So the first step is to relax all integer restricted variables, not one of them. We relax all of them. So the resulting problem becomes a linear programming formulation. The second step is to solve this LP. And since this is LP, from our earlier course, we know how to solve these. The simplex algorithm solves the linear programming formulation, so we can get a solution for the LP. Then, using the information that we get from this solution, in step 3, we add some spatial constraints into our original formulation and then resolve. And then, depending on that solution, we add some spatial constraint and solve it again. So there is a loop between these step 2 and 3. So we do these two steps iteratively until we find the best integer solution. Okay, so this is the general scheme how these algorithms work. And let's see examples of these. As I told you, in this series of tutorials, we will talk about the branch and bound algorithm and the cutting plane algorithm. We will first start with the branch and bound algorithm. The development of the branch and bound algorithm goes back to the year 1960s, and it's developed to solve either mixed integer linear programs or pure integer linear programs. So it can be used for both of them. In order to get the idea, let's have an example and let's learn the branch and bound algorithm using this example. So this problem is a maximization problem. We need to be careful with the objective, whether it's maximization or minimization, because from the relaxations, we know that whether the optimum solution of the relaxed problem is an upper bound or a lower bound depends on the objective function. So this is a maximization objective. Okay, then we have two variables, x1 and x2. Both of them are integers. They are not binary, they are general integers, so they can take values greater than or equal to 0, so they can take 0, 1, 2, 3, and etc. Okay, and we have two constraints. Let's have a look at the feasible region of this simple integer programming formulation. So this is our formulation, this is our objective function, and these are the constraints. This is the integrality constraint. So if we sketch, since we have only x1 and x2, we can sketch in two-dimensional axis coordinate system. So this one is the first constraint here, x1 plus x2 less than or equal to 5. So we are taking this side of this constraint. Okay, and this one is our second constraint, and since it's less than or equal to 45, again we are taking this side of this constraint. Okay, so x1 should be greater than or equal to 0 and x2 should be greater than or equal to 0. So the intersection of all these constraints is this shaded area. But be careful, the decision variables are restricted to be integers. So the feasible solution of this integer programming formulation is not the shaded area. The feasible region is only these black dots. Okay, all of these black dots are the feasible region of the integer programming formulation. Now remember, we said that in branch and bound algorithm, the first step is to relax. When we relax, what do? We basically get rid of the integrality constraints. Okay, so we delete this integer part, and the remaining formulation here is an LP. Okay, and the feasible region of that LP now is all the points inside this shaded area. And how can we solve this? By using the graphical solution method, we can easily obtain the solution. Remember, for an LP, the optimum solution will be on one of the corners. So the optimum solution will be either this one, or this one, or this one, or this one. In order to understand which one is the optimum solution, you should look at your objective function. 5x1 plus 4x2 goes in this direction. Okay, and since we are trying to maximize, this solution here becomes your optimum solution for the LP relaxation. And at this point, x1 is 3.75 and x2 is 1.25 and z is 23.75. So this is the solution for the LP relaxation. Okay, this is the end of the first step. But remember, our previous lecture, for a maximization problem, when you relax the problem and when you solve it, the optimum solution of the relaxation gives you an upper or lower bound. Now you should be able to answer this question. Since this is a maximization problem, okay, when you relax it, the optimum solution of the relaxation will give you an upper bound. Okay? So now we know that our optimum solution for the integer problem, for our original problem, will be less than or equal to 23.75. This 23.75 is an upper bound. Okay? We will make use of that information later on. After solving the relaxed problem, now we need to look at that solution and make a decision. Look, the values of the decision variables x1 and x2, they are non-integer. So we cannot use this solution as an optimal solution for our integer problem. It's infeasible for the original problem. Okay? So we need to somehow find an integer solution. So how do we do it? By modifying the solution space. So look at this feasible region of the LP relaxation, which is this shaded region, all shaded region here. Okay, so 3.75, x1 3.75, where is it? It is somewhere here, right? x1 3.75. So it means that, in fact, we can divide this whole region into two parts. One part is the left-hand side of this part, okay, and the other one is the right-hand side of this part, okay. So here x1 is equal to 3, and when we get the left-hand side, we have this region here, and when we say that x1 is greater than or equal to 4, we get this small triangle here. It's the feasible region. So you see, we ignore the region in between 3 and 4. Why? Because there are no integer solutions there. Look at the black dots. Are there any black dots in this interval? No. So in fact, what do? We divide the whole feasible region of the LP relaxation into two parts. We do not ignore any integer solution. We don't delete any integer solution, but we delete some of the non-integer solutions depending on the value of x1. Okay, so basically, since it is between 3 and 4, 3.75 is between 3 and 4, we say that the optimal solution, in the optimal solution, either x1 will be less than or equal to 3 on the left-hand side, or it will be greater than or equal to 4. But it can never be in between 3 and 4. That's why we divide. Okay, the original LP relaxation, we call it LP1, the first problem that we solve. Then, when we include these two constraints separately, if we include x1 less than or equal to 3 to LP1, then we get a new linear program, and we call this as LP2. It is this left-hand side in the feasible region. And if we include x1 is greater than or equal to 4 to LP1, then we get this right-hand side, and we call it LP3. We are not adding these two constraints at the same time. We are either adding this first one to get LP2, or adding the second one to get LP3. And we are going to solve LP2 and LP3 separately, find the best solutions in these, and then depending on that, we will find the integer solution. Let's continue. As I said, to this original problem, the feasible region of the original problem, if we include x1 less than or equal to 3 as a constraint, we get this left-hand side. If we include x1 greater than or equal to 4, we get this right hand side, and we ignore all the points in this region, and you see there are no integer solutions in this region. All the integer solutions are either in LP2 or in LP3, either on this left hand side or in this right hand side, and we will try to find the best of these. Okay, let's have a look at the models of this LP2 and LP3. We said that in LP2 we add x1 less than or equal to 3 to LP1. So what was our original problem formulation? We have this objective function, we have this first constraint, we have this second constraint. These are the constraints that we already have. Then we include x1 less than or equal to 3 as an additional constraint. And x1 and x2 is greater than or equal to 0. You see it's not written integer here because this is still a linear program. We don't have that integer. Okay, that's why we call it as LP2. And on the other hand, if we consider LP3 now, instead of saying x1 less than or equal to 3, we are adding x1 is greater than or equal to 4. So what happens to our model? Again, we have the same objective function. The first, second constraint is the same, but this time, instead of x1 less than or equal to 3, we add x1 is greater than or equal to 4. And still x1 and x2 are greater than or equal to 0 and non-integer. Okay, this is still a linear program. Now we have two linear programs, LP2 and LP3. We need to solve these. So let's start with one of them. Let's start with LP2. We have this LP2 formulation and we need to solve it. The feasible region of this LP2 is here. Which method can we use to solve this problem? If you like, you can use the simplex algorithm, but there is no need because it only has two decision variables, x1 and x2. Okay, you can use the graphical solution method. The optimal solution will be in one of these four corners. Remember, we are considering LP2, not LP3, so this is not included, only this part. Which one of them is the best? If you look at your objective function, it goes in this direction. So this solution is your optimal solution, in which x1 takes the value of 3 and x2 takes the value of 2. And when you put these two values into your objective function, you get z equals 23. Okay? This is the solution of LP2. We represent this branch and bound procedure graphically, so in this way. So we start with LP1. This is, sometimes we call it as the root node. Okay, root. This is, the name is branch and bound, branch like the branches of trees, and this is the root of the branch. So you can see that this is like an upside down branch. Okay, root is at the top and these are the branches. So we start with the first LP relaxation, which is called LP1, and solve it. And when we solved it, we got x1 equals to 3.75 and x2 equals to 1.25. And then depending on this solution, we said that x1, since it is between 3 and 4, we will include x1 less than or equal to 3 and x1 greater than or equal to 4 separately to obtain LP2 and LP3. Okay? Then for LP2, we solved that problem and we obtained x1 equals to 3, x2 equals to 2, and z equals to 23. Now we need to make a decision. Shall we continue to explore this LP2 more, or shall we stop at this branch? And the decision here is stop. Why? Because we already obtained an integer solution. x1, x2, the integer, the variables, although we solved a linear program, the variables appear to be integers. Okay? So what do? We stop here. When we stop in branch and bound algorithm at a branch, We call it fathoming, okay, fathom. So this is fathomed, and the reason of fathoming is to obtain an integer solution. This is, so sometimes we call it fathom because of optimality. But don't be confused. This is not the optimum solution of the integer program. We are not saying it. We only solved one half of the problem. The second half still remains. So we need to check for LP3. Without solving it, we cannot say that this solution is optimum. Okay? It's very critical. It's very important. Since we started with LP1, we give a number to these in these graphs. We call these as nodes. This is root node, and root node has the value of 1. Sometimes they give 0, okay, the starting node. And then from this LP1, we move to LP2. We selected LP2 and solved it. That's why we give the number 2 here. Then from this LP2, we need to explore LP3 also. That's why its number will be 3. Remember what was the problem in LP3? We are trying to maximize this objective function with this additional constraint, x1 greater than or equal to 4. At this point, you may have, in fact, two questions in your mind. The first question is this. When we solved LP3, the x1 value was 3.75. Okay, this is x1. And the x2 value was 1.25. And we said that, okay, since x1 is 3.75, let's branch on x1 and add a constraint saying that whether this is less than or equal to 3 or this is greater than or equal to 4. The question is this: why don't we use x2? Why don't we branch on x2? Can we use it? And the answer is yes. You can also branch on x2. And if you want to branch on x2, what you should do is, since its value is 1.25, you should say that x1 should be less than or equal to 1, or it should be greater than or equal to 2. Okay? And we will make example on this, or you can try this by yourself. Second question is this. Okay, we decided on branching on x1, and we included x1 less than or equal to 3 and x1 greater than or equal to 4. And we said that this one is LP2, okay, and when it's greater than or equal to 4, we say that it is LP3. LP3. So the question is this: can we first explore LP3 instead of LP2? Why did we continue with LP2? Can we continue with LP3? And the answer to this question is yes, you can continue with LP3 as well. But the thing is, the solution, you will get exactly the same solution. The optimum solution, objective function value, will be the same. But the procedure can take short or long. It depends on these decisions. Now we are going to solve the same problem, continuing with LP3. But as an homework, please try to solve the same problem by branching on x2 instead of x1 in the first step. Okay, try it by yourself. Of course, after finishing this tutorial. Okay, we already solved the problem. We got the optimum solution, but as I said, there may be different ways, different paths to reach to this optimal solution, depending on which LP you are going to solve first, or which decision variable you are going to branch on first. The procedure may take longer or shorter. So now forget about what we did until now, and let's solve the same problem from a different path. Okay, so assume the first step is the same. Relax the problem, find the LP relaxation and solve it. And when we solve that relaxation, you remember we get x1 equals to 3.75 and x2 equals to 1.25. Okay, and then we decide to, let's assume that we decide to branch on x1. So 3.75, we say that either x1 is less than or equal to 3 or x1 is greater than or equal to 4. Okay? Now, instead of first solving LP2, which includes x1 less than or equal to 3, let's consider solving x1 LP3, which includes x1 is greater than or equal to 4 first. Okay, let's start from this side first. What happens? What is changing? So when you solve this LP3, the resulting solution is this. x1 equals to 4, x2 equals to 0.83, and z equals to 23.33. Okay, now we need to make a decision. Can we stop for some reason? For example, all decision variables are integers. x1 equals to 4. It's integers. Okay. But x2 is not an integer value. It's 0.783. Okay, so we cannot stop. So we restarted. Okay, so there is no integer solution at hand now. We don't know anything. So we cannot stop because of bounding as well. So what we should do? We have to continue exploring. We have to continue exploring the value of x2, which is the fractional one. Okay, so let's do it. If we look at the branch and bound tree for this new version of the solution, we start from LP1, it's the same thing, and we got this solution x1 3.75, x2 1.25. We decide to branch on x1. Remember I told you that to try solving the problem, first branching on x2, not x1. Okay, you can try it. Okay, x1 is less than or equal to 3, and this takes us to LP2, or x1 greater than or equal to 4, and this takes us to LP3. Okay, now we will solve LP3 in the second step. That's why its node is numbered as 2. First node is LP1, we first solve it, then we solve the second one. So the numbers inside these nodes show us which node is solved in which sequence. Okay, and then when we solve LP3, we come up with this result. And since we cannot fathom it, we need to explore it. When I say explore, you need to branch it. So x2 is not integer, it's fractional, 0.83. So I need to branch on x2. And it's between 0 and 1, so I say that x2 is less than or equal to 0 on one side, and x2 greater than or equal to 1 on the other side. Now the question here, can we branch on x1 at this step? But look, the value of x1 is already integer, okay? It's 4. So we do not branch on integer values. We only branch on fractional decision variables. Okay? So what do we have now? We have LP4 and LP5. In the first one, we have x2 less than or equal to 0 and x2 greater than or equal to 1. Now look, in LP4, what do we have? We have the original problem, which is LP1. To LP1, in the first step, we included x1 greater than or equal to 4. And in the second step, we include x2 less than or equal to 0. So now in LP4 we have both of these constraints, okay, both of them. And in LP5 we have x1 greater than or equal to 4 plus x2 greater than or equal to 1, both of them. Okay, now what happens at this step? We have LP2, LP4 and LP5. We didn't make any decisions for these LPs yet. In order the algorithm to stop, all such nodes or branches must be fathomed. If there are some branches that are not fathomed, we cannot stop. We need to continue. Now we need to select one of these branches to continue, and let's select LP5. And as I said, in LP4, what do we have? On top of the LP3, we include x2 less than or equal to 0. And remember, in LP3, we have LP1 including x1 greater than or equal to 4. So we need to include x2 less than or equal to 0 to this one as well. So all the constraints on the branch and bound tree at each step we include. You need to include the former one as well. If you are going through a branch, all the constraints that are added until that time should be there. Okay. In LP5, again, on top of LP3, we include x2 greater than or equal to 1. But again, LP3 was including LP1 plus x1 greater than or equal to 4. So we include x2 greater than or equal to 1. Now, as I said, we have these three linear programs still open, still we didn't fathom them, and we are going to select one of them. Let's select LP5 and continue. Okay, what is LP5? LP5 is on top of our original LP, we include x1 greater than or equal to 4 and x2 greater than or equal to 1. Let's see what happens in our feasible region. Okay. So this was the original feasible region. And then in the first branching, we said that x1 less than or equal to 4 to have LP2 and x1 greater than or equal to 4 to have LP3. So this x1 greater than equal to 4 means that we are on this right-hand side. And when we solved that question, we found that x2 is 0.83. x2 is somewhere here. And then we are including now in LP5 x2 greater than or equal to 1. So what is x2 greater than or equal to 1? Let me sketch it with blue. Okay, this is x2 equals to 1. And we are saying that x2 is greater than or equal to 1, which means that take this part here. Okay, all these constraints, all the other constraints says that the feasible region is this small triangle. And then when we include x1 is greater than or equal to 1, you see this triangle and this constraint does not have any intersection, which means that this problem is infeasible. It doesn't have any feasible solution. Whenever a relaxed problem is infeasible, it means that the original problem is also infeasible. Okay? So remember, this LP5 is a relaxed problem for the question on the right-hand side, not for the whole part, for the right-hand side. Okay? So this x2 greater than or equal to 1, when we include it, we say that there is no feasible solution. That's why our decision is to fathom. Now, remember, we had remaining LP2, LP4, and LP5. We considered LP5 and decided to fathom it. The remaining two are LP2 and LP4. We need to continue with them. Okay, so in this branch and bound tree, where are we now? We said that we have LP2 still didn't fathomed, LP4 it's also still open. And for LP5, we have seen that it doesn't have any feasible solution, so we fathomed this one. So the only open branches or nodes are LP2 and LP4. So we are going to select one of them. We will select, let's select LP4 and continue with it. That's why the node numbers are 1, 2, 3, and 4. In fact, this is 7 because it will be explored much later. This is, in fact, the final, let's say, branch and bound 3. That's why it's written 7 here. In fact, you number the nodes whenever you explore them. Now we will continue with LP4 and we number it as 4. Okay, now let's consider LP4. We have these original constraints. On top of it, we have x1 greater than or equal to 4, which means that we are on this triangle here. And on top of it, we say that x2 should be less than or equal to 0. But also here, we have x2 greater than or equal to 0. So when you look these two constraints at the same time, it tells you that the value of x2 is equal to 0. Okay, x2 is equal to 0, and solve for the value of x1, and when you do it, the optimum solution becomes x1 equals to 4.5, which means that this corner is the optimum solution for this triangle in LP4. Now we need to make a decision. Can we fathom this one? And look at the values of the decision variables. X1's value is 4.5. It's not integer. So if there is a decision variable which is not integer, and if we cannot fathom because of bound or something, it means that you need to continue exploring. Now you can say that, okay, but we already included a constraint on x1 in which we said that x1 is greater than or equal to 4. And now here x1 is still 4.5. It is not integer. Can we add one more constraint on x1? Yes, of course you can. You should. And now in order to branch this LP4, we will say that x1 should be less than or equal to 4 and x1 should be greater than or equal to 5 because this x1 is in between 4 and 5. Let's see how we do it. In the branch and bound tree, we explored LP4, we solved it, and we have seen that x1's value is 4.5. So we include x1 less than or equal to 4 to obtain this LP, and we include x1 greater than or equal to 5 and to obtain this LP. By the way, this LP6, LP7, the numbers on LPs doesn't have any meaning. It doesn't include any sequence. But the numbers on the nodes are important. Okay? So the number here, 3, for example, says that it is the third node that we are exploring. This 6 will indicates that it will be the 6th node that we will explore. Okay? But the number here, this 7 here, for example, it doesn't say that it is the 7th LP that we are exploring. Now, LP6. What do we do for LP6? We include x1 less than or equal to 4. And until LP6, what we did on LP1, we first included x1 greater than or equal to 4. Then we included x2 less than or equal to 0. And now we are including x1 less than or equal to 4. And in fact, when you look at these two constraints, x1 greater than or equal to 4 and x1 less than or equal to 4 means that in the solution x1 will be equal to 4. In the next step, you will see it. Okay, in LP7 on the other hand, on LP1 we included x1 greater than or equal to 4, then x2 less than or equal to 0, and then we include x1 greater than or equal to 5. Again, when you look at these two constraints, if x1 is greater than or equal to 5, it means that x1 is already greater than or equal to 4. In fact, this constraint is redundant now. but it's not important. You can keep, it will give you exactly the same solution. Now when we have this LP6 and LP7, remember initially we already had LP2 which we didn't fathom yet. So LP2, LP6 and LP7 are the open problems. Then we need to continue with these ones. Okay, so let's select LP7 as the next one and let's try to solve it. When you look at this problem, okay, including x1 greater than or equal to 5, we see that x1 greater than or equal to 5 does not intersect with the feasible region, with that triangle. It means that this LP7 is infeasible. So whenever a branch is infeasible, we fathom it. So LP7 is fathomed. Now we select from this LP2 and LP6, we select LP6. Consider this LP6, this one. As I said, x1 greater than or equal to 4, less than or equal to 4. In the solution, x1 will be equal to 4. And we have x2 less than or equal to 0, x2 greater than or equal to 0. So x2 is equal to 0. And this solution is a feasible solution and it's an integer solution and its objective function value is 20. Now we need to make a decision. Can we fathom? And since all decision variables are integers, yes, we can fathom. And the reason for fathoming is fathom by optimality. Let's have a look at the branch and bound tree. LP2 still remains open, we didn't explore yet. We explored LP7 and we said that it doesn't have any feasible solution. So we initially fathomed L5. We fathomed LP7 as well because of no feasible solution. And then when we solve LP6, we found an integer solution. So this is important. When you have an integer solution, you need to be careful. Put a star for that because this solution now is the best solution that you have in your hand. Okay, this is the best solution. And what's its value? Its value is 20. Okay, so when you look at the LP1, we found that the optimum solution to this LP1 is 23.75 and it indicates an upper bound for us. And this is a feasible solution, 20, and it's a lower bound for us. And now we know that the optimal solution will be in between 20 and 23.75. But still, we didn't get the optimum solution. We cannot say that this is the optimum solution because there is one node, which is LP2, we haven't explored yet. And in the next step, we will continue with it. When we solve LP2, we get an integer solution where x1's value is 3, x2 is 2, and z is 23. Previously, we found an integer solution where x1 was 4, x2 was 0, and the z value was 20. And now we have a solution in which z value is 23. Now we need to be careful. Look at the objective function. What we try to do? We try to maximize, right? Objective function value is to maximize. And we get a solution with objective function value 20 and with objective function value 23. Which one is better? Of course, for a maximization, 23 is better. Then it means that you can forget about the previous solution. Now you have a better solution, which is this one. Okay? And the thing is, we need to make a decision. What shall we do with this node? The solution is, all decision variables are integers. That's why we say that fathom this node because of optimality, because of getting integer values. And since there are no other problems to be solved, we stop. The branch and bound algorithm stops. There are no other nodes. And what is the optimum solution then? The optimum solution is the solution that you keep in memory, the best solution that you get during this procedure, which we got in the last try, okay, with z value equals to 23. Then this is our final branch and bound tree. We started LP1 and then we branch on x1 less than or equal to 3 and greater than or equal to 4. Then we continued with LP3. Since x2 was not integer, we branched on x2 less than or equal to 0 and greater than or equal to 1. Then we continued with LP5, but we couldn't find a feasible solution, so we fathomed. So LP2 and LP4 was remaining. We continued with LP4, and since x1 here was not integer, we branched on x1 less than or equal to 4 and x1 greater than or equal to 5. Now the open nodes are LP2, LP6 and LP7, and we selected LP7 to continue. And this LP7, in this LP7, since we couldn't find a feasible solution, we fathomed. Then LP2 and LP6 were remaining. We continued with LP6 and we found an integer solution. All decision variables were integers with a z value of 20. So we put a star here since we got an integer solution, and we fathomed because this is optimal. All decision variables are integers. Then the only remaining node was LP2. We return back to this one. We solved it and we found an integer solution. Okay, since all decision variables are integers, we put a star here and we delete the earlier star because the objective function value of this one is better than this one. Okay. Be careful. If this z value here was not 23, but for example 15, we would still keep the old one. But since it is better, it is larger for a maximization problem, then we delete the previous one and we keep the last one. Okay, when we do it, since all decision variables are integers, we fathom this node, and you see there are no other nodes remaining, so we stop. And when we stop, the optimum solution is this. Okay. Now have a look at the two alternatives. Initially, we solved the problem like this. We solved LP1, the LP relaxation, and then we branched on x1 less than or equal to 3 and greater than or equal to 4. Then we selected LP2 as the next node. We solved it, and it was an integer solution. That's why we terminated it. Then we went to LP3, but since this 23 here was an lower bound for us, and since this 23.75 was an upper bound for us, we said that the only integer solution is this one, and we stopped. Which means that we terminated this LP3 because of bound. And that's all. We found the optimum solution in just 2 steps. But on the other hand, alternatively, instead of selecting LP2, if we select LP3, then we need to continue with LP4 and LP5, then LP6 and LP7, and then return back to LP2. And after that time we stop. And you see the whole procedure takes longer, a lot of steps. But the thing is, we don't know initially while solving, we don't know which one to continue with. We don't know if we continue with LP2 that it will take shorter or longer. So what do? We select one of them randomly. And there are some other rules to select, but usually we have no idea on which one to select. Okay? So we will continue with examples. This was the first example on the branch and bound. In the next tutorial, I will give you the formal steps of the branch and bound algorithm.